That's good news in a twisted way. Ready again? Airports. How many in here has been at an airport? I want to see some hands. Yes. There's a point to this. Okay, so you've naturally all been thinking about airports as places to go from one location to another. Welcome. But they're also kind of buildings filled with software. When you go through an airport, you trigger various bits in various subsystems in this airport. So it's kind of cool. It's a house that runs on software. I like the idea, or not house, a big building running on software. Welcome. That's CGA. I think it's the last one. Hi, I'm Masak. I talk about airports very seldom. I mostly talk about Carl 6 and things you can do with it, and various fun puzzles and games. But today I'm here talking about business applications. And this is a pattern. What I'm going to tell you is something that I found out in the last 8 months or so that I think is really cool, and I want to pass it on to you. So an airport consists of a land side and an air side. And they're pretty strict about security between these two parts because the air side is kind of sensitive. You don't want any kind of people moving around there, just people with valid tickets and so on. So this is a perfect application for software of some kind, checking everything and making sure that things are in a consistent state. So you start out, I'm going to describe a simplified system of an airport. There are surely variations of this. And if there's anyone in the audience who has actually implemented an airport, then please heckle me in the questions section, not during the talk. So imagine you're a passenger, you're supposed to fly, and you check in either by the counter or with a machine, and you get the ticket and maybe luggage tags and things, and you go and drop off your luggage. And then you enter this secure area, so you have to show your identification, and you have to basically strip down and decompose into various parts, and then put yourself together again. And it's a process of varying degrees of accumulation. And then you're in the secure area, and then you can go and board. And all these steps, you can imagine them triggering various phases or various states in the system. Everything, all these various steps, they matter to the system. It matters if you have dropped off your luggage. It matters if you're in the secure area. It matters if you have boarded the plane, and so on. So now we take on the role as software designers. We want to help some airport build this software system. And I'm just going to start by saying, if there's any single message, you're supposed to leave the message of the talk in the first 5 minutes. If there's any single message that I want to leave you with, the next time you're at an airport, I now post-hypnotically suggest that you think about this thing. It's okay to have more than one model. We tend as software developers to think, what's the model of this application? How should I model everything? And we cram all kinds of things into one and the same model, and it tries to please everyone, and it ends up pleasing almost no one. So it's okay to split your application up into various models that are sort of more specialized, and when you need to go from one model to the other, you focus on that instead, and the sum of all the challenges will be smaller than the challenge of trying to build a model for everything. Traditionally, what we do with these kinds of large systems is we start thinking about what data do I have? What is it that needs updating in the database or in the state of the application? So we start thinking about the nouns. What things are there? I see this every time. I bet you see this every time, all the time as well. Starting to think about passenger and flight and luggage as things in the model, and almost immediately you start thinking about them as tables as well, tables in a database. So it's really TDD, table-driven design, that we're talking about here. We're starting from the table and from the tables and from the database, and we let them drive the project. And not only that, we probably want to have some connection between passenger and flight, so we maybe end up with a booking table that just connects these two tables, sort of like a table that's only there for doing joins, things like that. And we have this idea that everything should be normalized. We're really happy about making things normalized, and we're really sad when things are not normalized, and we point to each other and said, see, I told you it should have been normalized, and we would have avoided all these problems. And today we're going to question that truth, and maybe some people will scream, but please scream in the question section. There's this sort of movement within software called domain-driven design that says that you should focus on the domain of the thing you're building. And there's this sort of slight focus on verbs, what you can do instead of nouns. So if we look at this from a domain-driven design perspective, what is it that we want to do with the model? Don't care about the data just yet. We can model that any which way when we're settled with what actions are there on the model that we care about. And you notice that these also fall into these various nouny categories. But that is a secondary effect. We really care about these are the actions that might matter to us. And we want to do this in, focus on the verbs. We want to do this in such a way that each receiver of actions, be it a passenger or a flight or a luggage object, they're pretty much independent. Because if we want to scale, we want things to be an island, sort of, not having any need to go outside of itself to return an answer, to make a transaction. So we make this sort of transactionally isolated super object. Think of aggregates as maybe one object, maybe an object with a lot of hashes and scalars and arrays inside of it, maybe an object with several other objects in it, so it's more of a hierarchy. But the main thing is that if you want to talk to this object, you go through the top object, what we call the aggregate root. And if this sounds to some people like facade, it does have its similarities, but here we focus entirely on the transaction boundary. It's not allowed to go outside of this object to find out, are we allowed to make this change? There shouldn't be relations between objects that affect whether we can do something or not. So it has to be an independent object. And yes, that means that sometimes we have to duplicate things. We have to copy things into this object just so that it has enough information to make decisions. For example, if I am a passenger, then the passenger object probably has information about the flight that I'm taking, and if it's a flight object, then it probably has information about at least the number of passengers and things like that. So there's some duplication of information, and that's what we have to sacrifice to make this aggregates thing work. There's also the notion of a bounded context, and this is also about transactional boundaries, but it is on a larger level. So now we're talking about the ordinary object level, the aggregate level, which is somewhat broader, and then above that, bounded context. You can think of bounded context as separate applications, really, but they're separate applications in the same system. So, for example, the passenger tracking is probably quite separate in the airport from the luggage tracking. It would surprise me, at least, if you need to sort of constantly keep track of the passenger while you're keeping track of the luggage. They're probably quite separate systems, and they could use separate back-end databases or whatever, and this would also help scaling. So traditionally, we end up with a multi-layered model looking something like this. And how many people are familiar with a model looking anything like this. Yeah.
I see plenty of clouds.
Sorry?
I see lots of clouds.
Lots of clouds, right. The cloud here just represents the net or whatever. You go over the net to talk to the server. So up here is the server. It has the data storage there on top, and every time we want to talk to the data storage, we sort of dress up this table information as objects in our application, and we can make queries to them, and we can make changes to them. When we make a query, we send up something called a DTO, a data transfer object. It's just an empty container with slots for all the values that we want to have back, and we get back a filled DTO with all these values. It's quite simple. When we want to make a change, we do something similar here. We send up a DTO with an existing object but with new values in it, or with an entirely new object that we want to store. And we get back an ACK or an ACK, depending on whether the operation succeeded. So very common view of things. And we get sort of bored of having to translate between these DTOs and SQL statements. So we most often involve an ORM of some kind to do the noun translation for us. So a service might look like this traditionally. You don't need to pay attention so much to the actual operations as the return types of the operations. Some things return void, and other things return objects, values of some kind. And what's different between these is that the void things do things, and the things that return things, they're passive, but they just give you back information. So we're really talking about two different kinds of method here, or whatever. We can split them up into two different services, one that does things and one that asks things. So one that makes queries and one that makes commands. And this seems slightly crazy from a traditional perspective. I mean, why would you want to have two services for this when it's acting on one model? What would be the purpose of this? And we'll see why in a short moment. What this division gives us, quite simply, is that we can formalize. You see what's changed in this picture now is we no longer send up a DTO here. We send up a command. We say, I want to make this change. For example, book passenger. It's no longer just an object containing loose values. It's a command that is named after what it does. So the command is book passenger. The best way to think about commands, according to me, is think of it as a method that you need to call on the server side, but it hasn't been called yet. So you make sort of an RFC thing, and you pass along a frozen object which represents this future method call. So if you want to call book passenger in the server, you pass along a book passenger command to the server. And as usual, you get back a yes or no answer, depending on whether it succeeded or not. So commands are, as of yet, uncalled method calls. And that's it. That's the CQRS. So the story would end here, except we go on to make this much more awesome. We now split up the server into two parts. One that takes care of writes only, and one that takes care of reads only. So we don't even need to struggle with these domain objects. So things like object orientation or anything. We just go straight to the database and pick up things out of the tables and dress them up as DTOs, which will make our reads faster. Suddenly we talk much more directly to the database. We don't have to go through the whole application just to get hold of some information from a table. This is much more direct. And then we start thinking, if the application is split into read side and write side, why not do the same thing with databases as well? And we come back to this point about being normalized. Why do people tell us that we need to be normalized? It's this eternal truth that we don't question. And we go back to the literature, and something that's been known since the 70s is this. Database intended for online transaction processing, OLTP, are typically more normalized than databases intended for online analytical processing, OLAP. So these kind of long terms with boring acronyms, it really means when you do writing, you should be as normalized as you want. When you do reading, you should be as denormalized as you want. Think of it. When you do writing, you want to touch as few places as possible. So if everything's normalized, it's don't repeat yourself, it's information in one place, you just go in somewhere and change that. When you do reads, you probably want quite a bit of repetition. You want things splattered out into long, broad tables, sort of everything joined with everything, so that you can just pick it up and you get the information as you want it. You don't want to do a lot of joins because that slows you down. So you see here, you don't need to be stuck with one model. You can have one model for the writes and one model for the reads. And reads are more common. What would you say in a certain blogging software or whatever? How much more common is it that someone visits the page, hopefully, than that someone makes a blog post? It could be 10 times more common, or 100 or 1,000 times more common. We really want to optimize for the reads. We want those to be fast. And with traditional applications, we really shoot ourselves in the foot there, because every read requires a complicated join just to get out the information. So now we have two separate databases for our system. We have the data storage for the write side, and we have events propagating over to the read side saying, hey, this just happened, update. And this means that as they are no longer the same database, they can even look quite different. The read side database can be optimized for what we want to do on the read side, which is read out information, large redundant filled tables. And you see that there's a new thing called an event going on here. So if a command was something that hadn't happened yet, an event is something representing something that already happened. So the write database is the master, and the read side database is the slave in this case. And the events are just propagating out information saying, hey, this just happened. You might ask yourselves, how similar is an event to a command? It seems that they could be quite similar, right? You pass a book passenger command, and out here you get a passenger booked command, and they sort of kind of contain the same information. And there are two considerations here. One is that it's about language. You say book passenger command, that's an instruction. You want that to be in the imperative. The event says passenger booked event, which means it's in the past. It's already happened. So there's a linguistic sort of constraint to make you write correct code there. You don't want to mix up commands and events because they're on different side of the transaction. The other consideration is that yes, they will start out the same. You will make a model which looks eerily similar on the command side and on the event side, but as your application matures, you will realize that these connections aren't as obvious as you first thought, and the commands and the events can evolve separately, and sooner than you think, you will end up with a model which is quite rich in its relations between its commands and events. It's quite possible to have one command trigger a bunch of events. So what is an event? We could think of it as some sort of a diff on an aggregate. So here we see a passenger aggregate traveling through time. We see the picture of the airport, but now represented as 4 events. The passenger books on the internet or something, checks in, clears security, there apparently was no luggage in this case, and then boards the plane. So each event here represents an update to some aggregate. And if you're a functional programmer, you think of this as a sum of some numbers, for example, just that in this case there are events instead. So you start from an empty aggregate and you by all the events in order, and the state that you end up with is the current state. So current state is just a left fold of the history of events, which means that we have a model which is not only as descriptive as the state model that we're used to, it's actually more descriptive because we're keeping every event around that we care about for the model. Now that we have a separate read side, we can customize the read side and say, hey, I have an RSS feed for my blog, for example. This RSS feed, it just gets updates every time I add a post. So I need to do something really simple and transform things to RSS and just update the already basically static RSS feed in my read side. And when someone comes and asks for the Atom or RSS feed, I can just fetch that statically from the database. I don't have to build it dynamically based on a number of questions to the master database. I can just have a read database specifically tailored to produce RSS feeds. And that goes for anything. You could build blogs this way, you could build indexing databases this way, and so on. You can basically make any kind of read side you want just based on consuming these events. So what it looks like now is we have these two databases up there. We have event handlers that take care of the events flowing in. Some events we might not be interested in at all, and some events we want to make some change in the database. And those are relatively simple SQL or whatever statements that you have to write on the read side, because you're basically doing point updates all the time. And you can have several read sides, and some of the read sides will be interested in some events and some others will not. So current state isn't always enough. Think of, for example, a banking system. You have your account. You have some money on the account. If you go to the bank and you ask, why do I have 42 euros on my account? And they don't say, well, because that's what the current state is. They bring you a long ream of paper saying, well, here are the recent transactions on your account. This is what you want to, this is what happened to your account. Do you disagree with this? So they actually store all the events that happened to your account, and I'll bet as they show you your current amount, what they are doing is actually replaying these events and showing you the current amount sort of played out from that. So banks do this, and we should do too. There's also the possibility, slight possibility, that we don't know what will happen to our application in 5 years. And for those of you who do know what will happen to the application in 5 or 10 years, feel free to make a static model that will be the same forever, and not make an event-based model where we can basically go back and replay the events anytime we want, and basically build new readers for the events as we go along. So we have information from the beginning of the system, and we can replay that and do something new with it. The boss comes to us and says, hi, I want to do statistics on customers to see which ones deleted an item 5 minutes before they made a checkout. And we can do that because we've stored all the events with timestamps and types of events and all the event data. If you're wondering how the application looks inside, as a command comes in to the application, what happens is it's greeted by a command handler, just as the event was greeted by an event handler. The command handler dispatches the command to all the parts of the application that care. And probably you want to change an aggregate in some way, which means that you need to have the aggregate at hand. The aggregate is in the data storage. The data storage is just contains the events. So you need to rebuild the whole aggregate from the start, from an empty aggregate and applying all the events. And then you can make a command on it. If you fear that this is slow, consider that the typical aggregate will have 10 or 20 or 30 events, and you'll just query those. You'll see the layout of the aggregates table soon. Compare that with doing a multi-join of 5 or 8 or 10 tables just to find one line somewhere in the table. I bet that it's faster every time to just query 30 lines in a single table based on an ID. So the command handler rebuilds the aggregate, as it were, and applies the command or rejects the command and sends a no back. And that's it. So the events table is very simple. If you want to represent this as SQL, which you don't have to, there are certain specialized stream databases that you can use because events are read-only. They apply once. They're like a tail-f. You add it once and you never go back and change it because events are immutable. They are something that happened in the history. So to represent an event, we have at minimum 3 things. We have an aggregate ID. Which aggregate did this event happen to? We have data, which is just one big blob of the whole event, kind of convenient. And we have the version. This is the version of the aggregate. So if it's the first event, it's version 0, and so on. This is to help against many clients coming in and making changes at the same time. So you can check the version and check the latest version and see if someone got in before you to make an event. So this is a very simple mechanism to prevent race conditions and things like that. The aggregates table, it looks almost the same. You see, not very much has changed there. We need also to store which aggregates are in the system. If this were a state system, we would store the data here, but we don't. We just store there's an aggregate with this ID. This aggregate has this type, passenger or flight or luggage. And this aggregate is up to this version as of now. And the last one is a slight speed saving because we could reconstruct this number from the history of events, just looking which was the maximum version saved. But we just store it here and make things go a little bit faster. So it's denormalization again. Now, the thing I said about aggregates, they're not supposed to go outside of the aggregate to look for information. We have a slight problem here. Well, dropping luggage is easy. It only affects the luggage aggregate, probably. Going through passport control and boarding the plane is also easy. You just update something on the passenger object. That's easy. But the check-in process, it touches everything. At least in the airline that I'm flying with regularly, it gives you the opportunity to book a seat on the plane, which affects the flight. It probably sets a state in your passenger object saying, okay, you're checked in now. And it gives you fresh new luggage ID stickers to put on your luggage. So we're in all 3 bounded contexts here, checking in. What do we do? Well, first it seems simple, and then it seems tricky, and then it seems simple again. This is the client doing this. This is either someone standing at a counter using a computer, or it's one of these cool new check-in automatic machines. The client can easily go to each bounded context in order and just do its things. Goes to the passenger bounded context and says, okay, this person is checked in now. Goes to the flight bounded context and says, oh, here are the seats that are free, please pick one. And it says, how many pieces of luggage? Oh, here are your tags. So the client has no restrictions on bounded context. It just looks like one single application, but sort of in the background, it's going to 3 separate subsystems. But the problem starts happening when you think about this. What if the client crashes in the middle of this? Then we have a problem with the consistency. The passenger aggregate is checked in, but it doesn't have a seat on the flight, so the seat count will be wrong. What do we do about this? We invent a nice concept called a saga, which is basically a small state machine sitting around. It's yet another subsystem, basically, listening to the events coming in and making high-level decisions about your application. So this saga will notice, hey, this passenger checked in but never chose a seat. That's erroneous. So we'll have something like this. If you studied automator theory, this will be slightly familiar. Usually the saga is in the start state. when it gets a passenger check-in, it's in the wait state, and two things might happen. Either the passenger will actually choose a seat and we win, or there will be a timeout event, which we generate somehow. That's no problem technically. And the timeout event after 10 or 20 minutes just says, oh, we timed out on this passenger. The client crashed or whatever. And we just go back to the start state, basically, saying, and invalidating that passenger booking. So a saga will bring us back the consistency that we lost from not having everything in a single model. So the advantage of having everything in a single model is that we can enforce consistency on that model. But now that we have a write side and possibly many read sides, the write side is sometimes slightly behind in sending out events. And you might be getting old information as well. One nice thing that I think on its own would sell this idea is testing. How many of you have heard about TDD? Not table-driven design, but test-driven design. How many here have heard about BDD? Okay, it's mattering. So the idea is really a formalized rehash of TDD. Instead of just writing a test, we write a test with some conditions. We break it up into 3 parts. Given a certain aggregate in the domain-driven design formalization, given this state, when we perform exactly one operation, we want these consequences to appear. And consequences might be either things that happen or an error that happens. But we start to look at these things that we have here, and we realize that an aggregate in a certain state, that's just a number of events that happen to that aggregate. So we can represent that as an array of events. An action performed on the aggregate, that's what we call a command. So we represent it as a command. And the number of consequences, that's saying the same thing as a number of events. So we represent that as a number of events. Now we have a totally statically defined test. This is just a test consisting of 3 parts, which are static immutable objects, really. They no longer contain any information, anything that runs. A test usually runs, but this is completely static, and we can make our cool little domain-specific language or whatever to represent this. Right, we have exceptions here as well, but that's no problem. Another benefit that this gives you is that you have basically 3 components of your system. You have the write side with the actual model, you have read sides, and any number of them, and you have clients that interact with this, be it a blipper at passport control or a check-in counter. And these teams can basically, these parts can basically be developed by single teams, as long as you keep in sync, so to say. So you always work on the same part of the application. If 1 week you're working on passenger, all of the teams are working on passenger, and they just check each other's progress at the end of the week. That turns out to work incredibly well, which means that you can be very agile about your project. You can start thinking about outsourcing in a way which you couldn't before. You can sort of outsource the client to India and outsource the views to Russia or whatever. And that turns out to work outstandingly well, since all the interfaces are defined between these parts. You have commands going from the client to the right side, you have events going from the right side to the read sides, and you have queries and the results going from the read sides to the clients. So modeling in this universe consists of describing the interfaces between these components. And that's what you start with, not with the tables in the database. So in summary, you should be okay with having more than one model. It's okay, it's great. Start thinking in terms of aggregates. They're also great. They make your application much more easy to scale upwards, because if you have aggregates and transactional boundaries, you have small independent pieces of your application, and the only thing you sacrificed was normalization, which doesn't matter anyway. Focus on CQRS, separating commands and queries, I never spelled this out, did I? Command query responsibility segregation. That's just the idea of having commands be one thing and queries be another thing. It's not all just GTOs all the way. Have a read side and a write side, because that makes you much more flexible in optimizing the write side for writes and the read sides for reads. Do event sourcing to communicate between these and to store the actual events in the model in the write side database, because that is a richer model than just storing the current state. You're not just storing what happened on the surface, but you're storing what happened all the way down. Thank you very much. I don't know how we're doing on time, but I'll be happy to take questions either here or Jonathan says 1 minute, so parts of a minute question. Yes?
Hi.
Yes?
Is there any stuff out there, any applications, frameworks where you may or may not be a fanboy of, but which implement a good chunk of these
Right.
quasi patterns?
I would recommend going and reading Martin Fowler's LMAX.
Sorry?
LMAX. If you just Google for Martin Fowler and LMAX, L-M-A-X, he has a really nice write-up, quite recent, I think, a month or so ago, about event sourcing and why it's good and why a team that needed to be very, very low latency and very high traffic ended up with this model just by experimenting and trying things that didn't work.
That's awesome. I actually was thinking of stuff in Perl.
Stuff in Perl. Right now, I would advise you to have a look at Jonathan and the thing that Jonathan and I wrote in Perl just to try these ideas out. It's a game server in Perl 5 Moose. And just go to my GitHub account, to Jonathan's GitHub account and find the project Hex there, and you will see Hex, H-E-X. There you will see a nice example, a nice minimal example that works, that you can run. Yeah. More questions? If not,
As I understand, most business logic will be between commas and elements.
right.
But if this commas will need to select data, this logic will need to select that data itself. So it will select it from event database, or it will need to have some long loop through another database.
Everything that you're interested in the business logic needs to be stored in the event database. If it's not an event, it means that you weren't interested in it. If you're interested in it, it needs to be an event. So everything that represents an interesting change to the system is an event on some level. Does that answer your question? There are no round trips to the read sites.